Let me start by thanking the organizers for organizing this nice meeting and allowing me to present here. So I'll talk about some topics which are very similar to the previous talk. So it's about random pinning in supercooled liquids, and I'll talk about its connection to random first order transition theory and the growing length scale. So this is the outline of my talk. I'll start with a basic slide on what is the glass transition and what is the random first order transition theory is, which you have already heard in the previous talk. Then I'll move on to random pinning and some of the results which we have in relation to R4 theory. So these are some pictures we have been seeing. Yeah, I just changed the color in the middle of the last talk. So this is the usual stuff. You supercool a liquid, and at some point its relaxation time becomes so high that it falls out of equilibrium and becomes a glass. And for theoreticians, the thing that we are mostly interested in is something which is called the ideal glass, which is the limit of this limit of these curves as the cooling rate is made to 0. And what happens is that in the supercooled regime, as you lower the temperature, the time scale becomes higher and higher, and the relaxation occurs via a stretched exponential decay. And there are various types of supercooled liquids, some which are called fragile and some which are called strong. The ones which are fragile have increase in activation energy with decrease in temperature, a dramatic increase, and for the strong ones, it's more or less constant as a function of temperature. So what is the random first order transition theory? So as you have heard in the previous talk, it assumes that in the supercooled regime, the supercooled liquid is made out of a mosaic of metastable states, and so each of these regions have a bulk contribution to the free energy, which goes like the configurational entropy times the volume of this region, and there is a surface cost of having a different region next to it, and that's the contribution of that to the free energy goes like the size of the region to the power theta, which is not necessarily d minus 1. And then from a balance of these two energy costs, you get a typical size of these mosaics, and that is given by 1 over Sc to the power 1 by d minus theta. And what is assumed is that the relaxation happens through activated processes, and the activation energy goes like the size of these regions to some power, and that power is psi. And so your relaxation time is e to the power the static length scale to some power divided by temperature, and the divergence of the time scale occurs because there is a divergence of the static length scale. And so this is the diverging mosaic size as you approach the ideal glass transition temperature. And this was introduced in these two papers, and this was reinterpreted in this paper. And so what is the static length scale? There are various ways to calculate the static length scale. The most popular one is the point to set length scale, in which so you saw a similar plot in the previous talk. So what you do is you freeze particles outside a spherical cavity and see if the region inside the cavity can forget its initial configuration, and the minimum size required for the supercooled liquid to forget its initial configuration gives you the static length scale. And then there is another length scale which can be calculated at low temperatures from the minimum eigenvalue of the Hessian matrix. So you just minimize the energy at from the starting configuration and see the vibrational modes, and the minimum eigenvalue of that, from a scaling of that you can get a length scale which also gives you the static length scale. And So this can be done at low temperatures, and then you can think of any quantity which has a finite size scaling, and you can do a collapse of that, and from that you can get a static length scale. And um, so any thermodynamic quantity, anything which is um, a property of the equilibrium state, you can do a system size scaling of that, and you get length scale. And this is, for example, the length scale obtained from the alpha relaxation time. And the problem with this, all of them, is that they all don't work in the entire temperature regime. So, for example, when the static length scale is too small, you need to do to see um, to see differences in your results as a function of system size. You need to do simulations of very small system sizes, which may not be very feasible. So you can't calculate the length scales for a high temperature in this way. This thing works at low temperatures. This thing works at low temperatures, and this thing does not work at low temperatures. It's very difficult to do at low temperatures, because any cavity you may construct will be smaller, much smaller than the static length scale, and for those situations this cannot be done. So basically, what the status is that the standard methods don't work at all temperatures in which we are interested in for the static length scale. So the systems we study are the usual systems, at least two of them. So the first one is the three-dimensional binary Lennard-Jones mixture, Cobb-Anderson mixture of two types of particles. And then we also study the two-dimensional version of it using 65-35 proportion of the big and small particles. And then we also studied repulsive systems which interact by repulsive interactions, 50-50 mixtures of particles interacting by 1 by r to the power 10 interactions, and a similar thing in 2 dimensions. So what is random pinning? So you take a snapshot and you select a subset of particles and you freeze them at their location, and so this is the particles circled are the ones which you don't allow to move, and then you observe the dynamics and see what happens. And so what we mainly focus on is the overlap correlation function, which is a measure of the fraction of particles which have not moved by a sufficient distance from its initial position after time t. And so this is the version for the system without pinning. And when you introduce pinning, you need to, the particles which are pinned by definition have not moved, so you exclude those particles, and this is the overlap correlation function. But in this case, you also need to average over the different realizations of the quenched disorder, the different realizations of the pinning, so these are the first results. So you calculate the relaxation time from the overlap correlation function, and then you can fit it to a power law to get the mode coupling transition temperature, or you can do a VFT fit and get the VFT transition temperature. And this fit also gives you a value of the fragility of the liquid, which was shown in the first plot, where I said that the activation energy for some liquids dramatically increase as you approach the glass transition temperature. A measure of that is the fragility. And so what we see is that as you increase the pinning fraction, the fragility of the supercooled liquid decreases. So the liquid becomes stronger, or in other words, the activation energy becomes well defined. So it becomes a weaker function of temperature than the unpinned liquid. So this is the main result which is obtained from this. We have similar plots for 2D, which I have not shown here. And so what we show is the plots below are the ones which may be interesting. What one would naively expect is that as you introduce pinning, since the dynamics becomes slow, the transition temperature might have increased. So here we show that it within error bar does not increase, and so we explain it saying that the fragility is the one which causes the slow dynamics and not the change in the in the transition temperature. So there are two ways in which you can make a liquid slow, and one is by decreasing the fragility or by increasing the transition temperature, and this is the fragility is the one which is responsible for the slowness of dynamics of pinned liquids. Then so this result has some controversy, and it's not agreed upon whether by thermodynamic calculations don't agree to this result, but yeah, this is what we get just by looking at dynamics. So the next thing we look at is how whether this construction of random pinning can be useful in any way. So one thing that can be done is that the relaxation time at when you introduce pinning and the relaxation time for the unpinned system can be collapsed by this functional form, where you have a length scale which is a function of temperature and it's not a function of pinning, and the pinning is just multiplying that, and so the ratio between this unpinned relaxation time and the pinned relaxation time can be collapsed by this form. And so we have later kind of so there is a ground for this. If you assume that the relaxation has a stretched exponential form, then a relation like this can be proved. So provided the stretching exponent is not a very rapidly varying function of temperature, and so this is a so the collapse is quite good. So that is one evidence that this scaling form is correct, and also the argument with the stretched exponential form kind of supports this. And so some relations which can be derived from the Arford theory. So one is that the Adam-Gibbs relation has to be modified. So if you just plug in the length scale into the formula for the time scale with the static length scale to the power some exponent, you'll get a relation which looks like this. The usual Adam-Gibbs relation is that the relaxation time is related to the configurational entropy by something like B over TSC, where this alpha exponent is not present. So in 3 dimensions, there is a lot of evidence that Adam-Gibbs relation holds good. So the alpha exponent is 1 in 3 dimensions, but it may not be true in all scenarios. So if you add the VFT relation to it, so which is there is numerical evidence that VFT relation is good for both 3D and 2D. So for that to happen, you must have that this thing in the denominator must go to 0 at the ideal gas transition temperature as a linear should linearly go to 0. So basically, if you have that, then you'll have the VFT relation. So also from the pinning data collapse, we have argued that this is true, and using these two and assuming that this so when you introduce pinning into the system, you are kind of restricting the phase space accessible to it. So its configurational entropy has to go down. So there are various ways you can model how it goes down. One is just by it goes down by an additive term. What we assume, which agrees with the results we get, is that the configurational entropy at non-zero pinning is related to the configurational entropy at 0 pinning by a factor which is 1 at 0 pinning and goes to decays as you increase pinning. So so if you assume that, then what you get is this T times the spinning length scale to the power D is 1 over SC to the power alpha, where SC is here is the unpinned configurational entropy. So, and also this has to be also equal to the static length scale to the power psi, which was in the Arford relation. So now, given this, so this would mean that this would mean that xi p to the power d was like 1 by t minus tk, and so this is kind of checked in this plot. And so what we plot is IP versus t minus tk in a log-log plot, and so these lines are x to the power minus 1 over d, and for the three-dimensional plots are very good, and two-dimensional ones also look reasonably good. And so, so what you see is this relation. So xi p to the power d goes like 1 over t minus tk. So, so next we try to calculate the exponent psi of Arford theory, and this is a part where at least for the 2D R10 model, the data is very noisy, and so if you had to get an exponent psi out of it, the values are these, and so the values are very close to 1 for 3 of these 4 models, and it's 0.7 for the other one. So once you have that, then you need to also verify the modified Adam-Gibbs relation. And in 3D, all data available is perfectly agrees with the usual Adam-Gibbs relation without that alpha exponent. And for 2D, the exponent you need for the 2D R10 model is 3, and for 2D modified Cobb-Anderson model, it's 0.7, which is not too far from 1. The fact that this is 3 will create some problem later on. So this is very not even close to 1. So so the modified Adam-Gibbs relation is the tau alpha goes like some e to the power 1 by t sc cube for the 2D R10 model. And so this is so the next thing that is useful is that the fragility of these different differently pinned supercooled liquids can be explained using one length scale. So what we do is we assume that the form the tau alpha being equal to some e to the power of xi s to the power psi over t to be true in the presence of pinning, and from that we extract the static length scale in the presence of pinning, and if you use that, these so let me mention that this is a way to display the variation in fragility. So for a strong liquid, if you plot this kind of plot, so if you plot tau alpha versus 1 over t, and the y-axis is a log is taken, then you'll get a straight line, and the fact that it deviates from the straight line shows that there is fragility, and how much it deviates gives you a measure of fragility. And so using the static length scale in the presence of pinning, you can collapse this data, and kind of so this kind of shows that the static length scale is all has all the information of fragility in it. So yeah, that's these plots. Then what about the surface tension exponent of Arford? So the surface tension exponent now can be, so now you have two of the, so you have the relation that alpha was equal to psi over d minus 1. So sorry. So you have alpha is equal to psi over d minus theta. So from that, now you have two of these 3 numbers, and from that you can calculate the surface tension exponent. And so for the 3D models, the 3D R10 and 3D KA, you see that theta is very close to d minus 1, and for the also for the 2D modified Cobb-Anderson, the theta comes out to be very close to d minus 1. But for the 2D R10, you get some result which is kind of very difficult to explain, and its theta is 1.7 where d is 2. So it may mean that Arford is not valid for 2D R10, or some modification has to be made. Some steps may have to be modified, but this is what we get. So these are the main messages of this this work. So so what I have talked about is that so there is an easy way to calculate the static length scale which works at all temperatures, and it's not very hard to do, provided you can do the unpinned simulation at that temperature. It's very easy to get the static length scale at any temperature you want. Then what is also shown is that suppose you have suppose you know the static length scale that is there in the system, the fragility of the liquid can be explained, and so this is kind of what many people expect, but it has not been quantitatively proved or disproved, and then so for 3 of these 4 model systems we tested, this R4 theory works, and then I'll talk about since I have some time, I'll talk about something which we continued doing. So this is something which is called soft pinning. So suppose instead of pinning these particles rigidly, you do it in a softer way. One way of doing that is introducing bigger particles. In that case, we have shown that. I'll just go to the next slide. So, so in that case, you can construct something called, even in the usual case, you can construct something like called the pinning susceptibility, which is a measure of how much your overlap correlation function changes when you introduce pinning. So this is the formula for that. And so when you plot this quantity, you get something which looks like this. And then what we can show is that for the usual pinning, the strict pinning, you can get the pinning length scale out of, so the maximum of this this quantity gives you the pinning length scale to the power 1 over d. So that can be shown and from the scaling collapse relation, and so this is verified here for the 3D Cobb-Anderson model. I have not, we have done it for the other models as well, but this is what we get. And the more useful thing is in 3-dimensional structural classes, it's very difficult to do these random pinning in the way I was talking about. It can be done in these colloidal experiments, but in 3-dimensional, suppose you want to pin a particle in the middle of the liquid, it's very hard. So instead of doing the strict pinning, you can do a softer pinning where you introduce some big particles which are kind of slow particles which are almost like pinned particles, and if you do that and construct a quantity which is like this pinning susceptibility, then you actually get the static length scale out of it. And so it's a way experimentalists could calculate the static length scale in an arbitrary liquid just by introducing some big particles in it and see how much it affects the relaxation dynamics of the system. So this is something which has been done, and yes, so you are in the limit of small number of impurities. So if once you go to the regime that it affects the static structure a lot, then you need to stop before that. So yeah, so if you so the assumption is that for small so the question is that if we put in these big particles, then the static structure factor of the remaining liquid changes, because these particles are occupying some, they need some place to go to, and so will that affect all the results? So I would assume that in the limit of small number of big particles, it wouldn't affect the results. Yeah, that was the last thing actually. Yeah.
Okay, questions? There's some time for questions.
Abhishek, this last thing that was mentioned about having the big particles.
Yes, yes.
Would you have a problem with depletion then? Because the big particles will come together and that your system is evolving.
Yes, so yeah, that's a related question, but so yeah, as Shorajit said, one thing that was done is the density was not affected, the overall density. So, so it was done at constant pressure, these simulations with the big particles. But other than that, yeah, it will affect when you have a very high number of big particles, but we assume that in the limit of, so whatever we are extracting is the limit of small number of big particles. So it's about double the size of. So it's you can.
Interesting.
Yeah, that also we tried. The mass. So the mass. The problem is that the energy landscape stays the same because suppose you did Monte Carlo or something else in which so mass actually affects the dynamics. Yeah. So yeah, that can also be. We have not analyzed the mass simulations in great details, but yeah, that has also been.
So, Suresh, I guess in all this R-Fort analysis, one of the big confusions, I guess, is the values of the exponents, what they should be and what people find. Right?
Yes.
So you did mention various things, but at the end of the day, in terms of the exponent, when you mentioned that the
modified
the theta didn't look right for one of the 2D systems, but other than that, what, so like the psi exponents
was very close to d
is
minus 1.
Sorry?
They were very close to d minus 1.
The psi.
So which one? The psi exponent.
Psi.
The psi exponent was actually close to 1 of the order of 1 for all of them. So it was like 0.7 for one of them and 0.91. So it was like so.
No. How sensible or violating some other sort of.
So the psi exponent just says that the activation energy is psi to the power as the static length scale to the power psi. Yeah, so it's there is no understanding of that other than R-Fort. So it's just an assumption that the activation energy goes like psi s to the power psi. Like it's a it has.
Yes, so I have a much more naive question. I think I missed something completely. So you said that when you increase the pinning, the fragility decreases, right? So the glass becomes stronger and stronger.
Yes.
If you think in terms of the activation time scale.
Yes.
So what does it mean? It means that the exponent alpha is going to 0?
No, the exponents are staying same.
So if you look at the expression for the tau alpha, right? You've got something like exponential, a constant divided by t times the conventional term for alpha.
Yes.
If you want this to become Arrhenius?
Yeah, it'll, so yeah, just.
Probably I missed completely something. So essentially, why is the.
So the VFT relation is best to start
towards Arrhenius behavior.
Yeah. So this, the VFT, the usual VFT relation is, I think it's best to think about it in the fragility constant into 1 by t minus minus 1, right? So what we say is that this thing is changing. So you can think about this. So this is equal to e to the power ESC to the power alpha. But I think it's easier to think in terms of this formula. But if you want to think about this, then yeah, it can be. Even without alpha changing, the whole thing is happening in terms of so this TSC to the power alpha is T minus Tk times a prefactor, right? So we are saying that the prefactor is actually changing and not alpha and Tk and all those things.
Okay.
So the theories are saying qualitatively similar.
Okay.